how many of you have, so for the newcomers who just joined us, welcome. I just wanted to quickly check. Everybody has access to the Slack channel? Yes? Network Science? It's on the Slack, big Slack that we have for the conference. We're going to use the Slack channel for the people who feel shy and you don't want to raise your hand and ask me a question in front of everybody else. Then go ahead, use the Slack channel, perhaps someone else can answer. And during the downtime that I will have, when you will have longer exercises, I will be able to check in on the Slack channel and figure out where people are, where people's questions are. So second thing I want to check for the newcomers who just joined us, your environments are okay? Python environment's okay? Check env script worked fine? What I would like, if everything works fine, then what I'd like you to do is one final check pre-tutorial, which is open up. You'll notice that for the main content, there are some notebooks that have an instructor and a student version. Pick any one of those at random, open up an instructor version of the notebook, and run all the cells just to make sure everything runs perfectly fine. Okay? Now, if for whatever reason something crashes on your local machine apart from your computer, there is a static HTML version of all of the notebooks available on GitHub pages. So if you feel tired and you don't, this is the sunset tutorial. So if you feel tired, you don't want to code on the exercises, I won't be offended. Feel free, go ahead, follow along using the instructor notebooks or the static HTML versions, which are the static HTML versions of the instructor notebooks. All right? That's it for now. That's it for now. So we'll get started. We'll get started at 5 minutes after. We'll follow university time. Finally we meet. Okay. To 4 p.m. So break time will be at 2:15. What's my timings again? Oof, pushing it.
I know, but the room just it's a bit small.
Okay. Okay. Okay, so for those who just came in, just want to check. I'm going to repeat myself for a second time. Make sure, are your Conda environments all set up? For those of you who just arrived, everything's okay with your Conda environments, or your Python environment, sorry. Okay, good. Next up, please fire up your laptops, run an instructor notebook, just to absolutely check to make sure. This is the last minute check before the tutorial starts, so make sure you pick an instructor version of one of those notebooks and run all of the cells inside there, and this will serve as a double check. And if there are any issues, this would be the time to catch them. If you have, if for whatever reason your notebook crashes and you're unable to follow on, or if because this is the sunset tutorial and you're thinking of just relaxing and just following along instead, feel free to open up the instructive versions of the notebooks to follow along if you don't want to do any more coding exercises, and I won't be offended because I totally understand. That's how tutorials are. Mine network analysis tutorial was was also a sunset tutorial once at a PyCon, and people got really tired at the end. So I totally understand the sentiment. That said, if you don't want to code or something crashes, you can follow along with the static HTML versions of the Jupyter notebooks. They're all available on the GitHub repository on my GitHub page. And for those of you who have already done all of the pre-checks, I think I've got a notebook 0 called Coding Exercises. Just check what the exact name is. Pre-tutorial exercises. It's just to warm up. But then if you were in like a tutorial this morning, you're probably warmed up as well already. So feel free to skip that or do it at your own leisure. Yeah. And I want to very quickly check who's using legacy Python. Not by choice. Okay, good. No judgment there. But you have an environment with new Python? Okay, no problem. No worries. If there are any issues, just let me know as well. All right. Nobody else using legacy Python? That's right, 3.3. 2.7. We all know Python 2 is end of life in 2020. So be sure to be catching up. The community's moving forward. Python 3.5 has the matrix multiplication operator, which is really cool. Python 3.6 has f-strings, which are even nicer. So, new features being added to the newer versions of the language. Be sure to catch up. Okay, let's see. We'll wait 2 more minutes before we get started. All right, let's get started. All right, we're at university time, so we're 5 minutes after we're supposed to start. So we'll start at 5 minutes. So welcome. How are people feeling today? Thumbs? Thumbs if you're good. No if you're feeling really tired. Okay. What if I said my goal at the end of this tutorial is to make you all feel really, really, really tired? That's not the purpose of this tutorial. You all are here for network analysis. This tutorial is called Network Science Fundamentals, basically. And so it's based off the GitHub repository, which is Network Analysis Made Simple. It's a collection of content that I made during my graduate school tenure. And now that I'm done with graduate school, this has taken a life of its own, and people have started contributing in many ways, big and small already, so I'm really happy about that. So in my own time during grad school, my thesis work, I had to teach myself a bit of graph theory, network theory, to get my stuff done. And so that's why this material exists. And it's my pleasure to share it with everybody today. Now, this is a tutorial that will involve a lot of coding exercises. Intentionally, it's structured not as a 4-hour lecture, right? And so I'm sure nobody would want to sit through a 4-hour lecture. There's a lot of coding exercises. There's one notebook that is particularly mentally taxing, so brace yourselves for it. It's going to be a lot of fun, though, because when it comes to network problems, the way I see it is as such. There are lots of puzzles that we need to solve when thinking through network problems. And in the early days, people thought through some of these, and so I'm going to guide you through some of these problems that the early days people thought through. For example, finding paths and finding, friend recommendation systems, closing triangles, and that sort of stuff. And so we'll think through the algorithms, and hopefully that will serve as an anchor for you to be able to think through other network-type problems when you're going through whatever network and analytics problems that you're thinking through. At the same time, I'm hoping it'll be a good introduction to NetworkX, one really good library with a very good API. And we cannot, NetworkX is good for solving, I guess, the Pareto principle type of problem. So NetworkX will get you 80% of the way. And if you have like tougher requirements, there's always alternatives. And I'm happy to talk with you about this after the tutorial as well. Okay, so like I said, this is a tutorial that will involve quite a bit of coding. So if you open up Notebook 1, if you want to follow along, you don't have to. This is mostly stuff that's on the screens. If you open up Notebook 1, you'll see there's a very short quiz. And this is intended to just make sure people understand a very common coding pattern. So we have a list comprehension that reads as such on the screen. Can anybody tell me what a plausible structure for S and my favorite things are? Popcorn style, raise your hand if you have an answer. For S or for my favorite things? S could be a dictionary, okay. And what about my favorite things? Any iterable. All right, so this is not a trick question. I wasn't intending this as a trick question. Basically, you're going to see a lot of this. You're going to see iterables containing dictionaries. And that's an idiomatic thing that I see for programming with NetworkX and Python. Okay, so let's first talk about networks. Networks are networks are prevalent all over the place, right? We have the thing that falls under, what is it? Maslow's hierarchy of needs, called the internet, right? So Maslow's hierarchy of needs apparently now includes internet connectivity, Wi-Fi connectivity. So the internet is one big network, right? And it's a very useful tool to model complex relational problems, all right? So when you think about your data, most of the time you're talking about samples from a population. We're taking one sample here at a time, and then we have this big data matrix. Each row is one sample, and I have all the attributes of the samples. When it comes to networks, it's no longer just about the individual samples, it's also about the relationships between those samples. And so when we talk about networks, or when we talk about graphs are the other term that I'll use prevalently throughout this tutorial. They're mainly comprised of two things, two entities. So there's a node list or a node set, and these are the entities. These are your samples in your data matrix. If you look at the network literature, you may notice they have the other term for nodes, which is vertices. So they're equivalent terms. And then you have edges, right? So edges denote what the relationships are between these nodes, all right? So edges are really important. In fact, I would consider, well, not me. There's this professor at the Harvard School of Public Health, and I agree with him, that the heart of a graph lies in its edges, not in its nodes. All right? So the heart of a graph, or the heart of a network, lies in how things are connected in it, and not in the nodes itself. Not what things are connected. Not the things that are connected, but how they're connected. All right? That's the main point here. So that's something that I'm hoping will be your highest level takeaway from this tutorial. That is, when you look at data, you're not going to just look at the nodes. You're going to start thinking about the edges in that relate these nodes together. All right, so let me check here. So I gave one example of a network, which is the internet. What are other examples of networks that you all know of? Pardon me? So a social network of such sorts. Anything else? Pardon me? Who's saying it? Ah, there, sorry. Monetary transactions. So what are nodes and what are edges? Okay, so we're talking about, say, banks. So the nodes are bank 1, bank 2, bank 3, and there's money moving around, and so they're related by the amount of money that's moving around. That's a good example. Streets. What are the nodes and what are the edges? Yep. Yep, so Google Maps, I believe, is one big giant graph. What else? Biochemical pathways. Yes, someone does biology. Tell me what are the nodes and what are the edges? Okay, that's right. So this is one of my favorites, actually. So proteins or enzymes. These are doing stuff to small molecules, and the small molecules get passed from enzyme to enzyme to enzyme. So the small molecules, which we might think of as an entity, they are actually the edge. They're not the node. And that's a very cool representation of data. What else is there? Oh, another biologist, yes. So gene co-expression networks, what are the nodes and what are the edges? So correlation by some metric can be encoded on this big matrix of gene by gene, and that turns out to be a network of co-expression in for genes. Cool, so yeah, those are examples of networks. People, curiously enough, didn't bring up Facebook, which always shows up in previous tutorials, and I'm glad for that because it means we're thinking about networks beyond Facebook. So Facebook is one big social graph, as is Twitter, right? And actually, that raises a good point here because there are two types of graphs, right? There are two types of graphs that at a basic level, and graphs can either be directed or undirected. So now if you think about the underlying data model for Facebook and Twitter, what would you consider Facebook to be? Would you consider it to be directed or undirected? Undirected, and why is that the case? Automatically. A bidirectional edge is automatically created anytime someone connects with another person. Now what about Twitter? Why is it directed? But then I might not necessarily follow you back, and the relationship is not immediately reciprocated, right? So that's the difference between a directed and an undirected graph. In an undirected graph, there's no notion of direction. Information flows bidirectionally if there's information flow on the graph. Relationships are automatically bidirectional. So actually, that brings up another point. Would we consider Google Maps to be, or rather our road network, is it directed or undirected? It would be directed, but undirected in most cases, right? You'd have automatic bidirectional edges by nature of how we build roads, but some of them are one way, and you can't get out of that scenario. So yes, okay. So that's the distinction between a directed and undirected network. It becomes important because there are some metrics that we define for graphs that work for undirected networks, but don't work for directed networks. All right, and later on, hopefully, you'll get to see some examples of that. Now, by the end of this tutorial, it's my hope that you'll be equipped to use NetworkX to construct graphs. You'll be using the Jupyter Notebook environment a lot, so hopefully you'll get familiar with that. We'll be showing you some network visualizations. Some are really bad, like hairballs, and I hope you all stay away from them. I'm very opinionated on this issue. There are other better ones that other people have designed and I've implemented in a library called NXViz, and I'm hoping you'll all use NXViz because those are rational network visualizations. My I'm also hoping that you'll be able to write basic algorithms that operate on graphs. So you don't have to necessarily write recursive functions. This is not a CS class, but be able to think through a problem in a recursive fashion and then implement something in Python that will solve your problem. All right. And finally, we'll be looking at some basic network statistics. So summary statistics about a graph, and we'll show you some examples. Now, as mentioned earlier, because the heart of a graph lies in its edges, my hope is you will eventually start thinking in terms of edges, relationships. You'll start thinking through relational problems, not relationship problems, relational problems. All right? Okay, so the format. I've alluded to this earlier on. There are, for the main content, there are two versions of the Jupyter notebooks. There's the instructor one and the student one. Clearly, you are supposed to use the, student version. You're supposed to use the student version, but if you feel tired and don't want to code, or you just want to follow along, have a nice chill sunset tutorial, then go ahead, open up, follow along using the instructor versions. Okay, for those of you who are fast and you find my pace too slow, feel free, go ahead, jump forward, solve the problems below on the notebook, solve the next notebook. I won't be offended. Totally your call. Okay, so with that, I'd like everybody to open up Notebook 2, which is a very quick whirlwind tour through the NetworkX API so that you'll be able to solve problems with NetworkX. So let's get that open, Notebook 2. And just give me a quick thumbs up when you're done loading that notebook. All right, we'll use this pattern here so that I can have a visual feel for everybody's progress. Cool. So we're gonna, as I mentioned, we're gonna use NetworkX, and NetworkX has a really nice API for querying and storing and manipulating graphs, and so we're gonna go really quickly through this. Okay, first off, a little bit about the underlying data model for NetworkX. It's dictionaries of dictionaries for nodes, and dictionaries of dictionaries of dictionaries for edges, and thankfully it's not dictionaries all the way down. But if you are familiar with dictionaries, you will understand why the dictionary accessor, the selector syntax with square brackets, gets used a lot inside NetworkX. So what we're going to do, so keep that in mind as we go forward. We're going to load some data. And so I've got so there's this really nice repository of data called the Connect Network Analysis Repository, Network Data Repository. And in this repository, there's this really nice real network data that's small, that'll help us get a feel for the API. So this data set that we're going to load is a study of 7th grade students. This is a directed network that contains ratings between kids, basically. So there are 7th grade kids. They were asked, who's your favorite person in class? And they would point. And they got 3 chances to do it. And so you can imagine this is like a social network of 7th grader kids. So what I would like you to do is to load the 7th grader network by running this cell over here. All right. Okay, so let's start first with looking at the graph. When we look at a graph, we need to know, ooh, something's going wrong with my notebook. Never mind, I have all the answers, so it's all good. When we look at a graph, the first thing we need to know is how many nodes and how many edges exist in the graph. And we want to know what are the nodes and what are the edges, how are the data being represented under the hood. So the first thing that we can do is we can ask, which nodes are present? And to get that, we would do g.nodes. So if you run that cell will execute and it'll give you back a list, effectively, right? So this guy over here is a list of nodes, and you can see that the students have been anonymized for their privacy from 1970 or 1980 or something like that, and they all have digits representing who they are. And because it's a list, I can use the list slicing syntax, and I can subset lists using, so 0 to 5, just show the first 5 nodes. So what I'd like you to do is very quickly write a single line of code that returns the number of nodes that are present inside the graph. And when you're done, give me a thumbs up and I'll know you're done. This is not meant to be a trick exercise. Nonetheless, I'll just give people 1 minute as promised inside the exercise prompt. Okay. All right, so everybody has this, len g.nodes, right? So that this being an intermediate Python tutorial, I'm sort of expecting that you know how to calculate the length of an iterable. All right, so there, you should have 29. Now, incidentally, because the graph G is essentially a dictionary under the hood, you actually can do len of G. So give that a shot. Run this with me. Oh, sorry. Well, I added some nodes later on, so it's actually 31 for the later one, but you should get 29 at this point, right? Everybody got 29. Okay, good. So next thing, we know who's present inside the graph. Now we want to know how they're connected. So we have a .nodes function. Correspondingly, we have a .edges method as well. So you can do g.edges, and I've sub-selected the first 5 edges. Can anybody tell me what this data structure is? A list of how many? A list of what tuples? 2 tuples, exactly. Okay, so this is how edges are represented. You have the first node, the second node, they're encompassed in a tuple. You have a list of tuples, and that's your edge list. All right? So what I'd like you to do now is write a single line of code that returns the number of relationships represented, number of edges inside the graph. So go ahead, 1 minute max. Write that line of code. When you're done, give me a thumbs up. And I see some people already thumbs up. Okay, so do people have len of g.edges as shown on the screen, right? Should be able to do that. So that will return the number of edges that are present, and you'll notice that it's a 2 tuple with this particular form of g.edges. Now we're going to complicate this a little bit, and we're going to see how we can retrieve not only the nodes, but also their metadata, and not only the edges, but also the edges metadata, all right? So if you scroll down here, if you do this thing where you go g.nodes and you pass in the keyword data equals true, that will return this kind of a data structure. So what's this data structure over here? It's a, nope, it's a list of 2 tuples containing an integer and a dictionary. That's right. We have to be pedantic about this. So that's how you get all the metadata. The metadata is stored as key value pairs in a dictionary. And that's why it's a dictionary of dictionaries for nodes and a dictionary of dictionaries for edges. So if you can, now that you know this, what I'd like you to do is to count the number of boys and the number of girls inside the classroom. So not this classroom, but the little classroom that's represented here. And as a hint, if you'd like to import counter from the collections module, which is in the standard lib, go ahead. That might make things a little easier. When you're done, give me a thumbs up so I can see. Okay, give people a bit of time. buttons popping up left and right. Okay, just a quick check. Those who finished, please raise your thumbs. All right, we'll give a hard stop at 158. And if you're done, you can also test your answers by running that cell. Okay, feels like people are done. So you should have something like that. If you use the collections counter object, you can grab out using the list comprehension all of the gender values that are stored on every single node. All right, that's basically how this was done. Okay, you can likewise do this for edges, and so to be pedantic about this, this is a list of 3 tuples containing 2 integers and a dictionary. Yes. Okay. So now that you know this, go ahead and figure out the maximum number of times that any student rated any other student as their favorite. If you read carefully the description at the top, you'll notice the answer should be 3, but if there are any errors in the encoding of the data, we should find that out over here. So find the maximum and basically check that it's 3. Quick check who's done. Okay, we'll do a hard stop at 201. Okay, so you should have something that looks roughly like this. The main idea is we can, again, do a list comprehension, iterate over all of the 3 tuples. And so if we do the tuple decomposition, or what do you call this thing actually? The tuple expansion, forgot what it's called. If you decompose the tuple into 3 variables, your third iterable variable D will be the dictionary, and so you can access the count variable there. Okay, so final piece is a little bit of something to get you familiar with the NetworkX API for adding or manipulating graphs. And so what I'd like you to do is to attempt this following exercise over here, which is to add some individuals and add some edges between them. And to figure out what the API call you need is, I think I provided the starter example there, and so you can copy that. In addition to that, you can also look at the NetworkX documentation link down there. Right? So we'll give people about 5 minutes to get this one done. Question? It doesn't. So what it does is if there's something if a node is already present and you add in a new node that has the same value, it will silently overwrite that node. Okay, quick check. How many people are done with this exercise? Give a thumbs. Okay, we'll do the hard stop at 2:06. Just a hint for those of you who are still on it, make sure you add the edges both ways because this is a directed graph. Yep, yep. Though you do lose the chance to add metadata to the nodes if you do add the edges directly. Yeah, set the node, access the node, g.node, select that node, and then add in a key value pair. Yes. I think they'll be there. Though in general, I think it makes a lot more sense to add the node first and then add the edges, so you're not implicitly doing things. Okay, 1 more minute. Or actually, how many people are done? If we're at 80% quorum, we'll move on. That's usually, okay, I think we're about there. Let's move on then. So you should have something like this. It's a little verbose, but this is like the elementary API call that you would make to add nodes one at a time. They have analogous add nodes from, pass in a container, pass in a container of dictionaries to add in the metadata, and that will work as well. And you can do the likewise, you can do it for add edges from, add in, and you pass in 3 tuples, a list of 3 tuples, and that will add in the edges plus their metadata dictionary for the edge. All right? Okay, we have a bunch of tests. Down here, when I first made this material, I was really passionate about tests. I'm still very passionate about tests. Write tests for all of your code. Write tests for your data. Check your data. Make sure your data makes sense. So that's a little bit of exploratory data analysis on graphs is what we've done here. So for example, checking that max count is 3, or checking that the genders of each student has been labeled correctly and that sort of thing. That's all important checks that we can do. And the NetworkX API gives you a way of accessing that data. You'll also notice that some of the coding patterns that become prevalent when you're working with NetworkX include list comprehensions iterating over 2 and 3 tuples, right? So make sure you know how to do this kind of thing. All right, we're going to move down to the section on drawing graphs. All right, so when it comes to drawing graphs, this section here is a little bit of me trying to do some promotion of rational visualizations and trying to discourage people from using hairballs. So we start then by introducing hairballs as a mode of visualizing your network data. And you'll notice it's really kind of difficult to interpret that thing with the exception of this little set of nodes that we've got up here, right? So these are essentially number 31 and number 32. So yeah, or number 30 and 31. NetworkX's built-in drawing capabilities lets you add labels to your nodes. So if you have small labels, they fit inside a circle, feel free to go ahead. Really, the NetworkX draw capability, in my opinion, I would only use it for graphs or subsets of a large graph that have no more than, say, 10 nodes. Beyond 10 to 20 nodes, you get into this land where it's hard to interpret what's going on inside the hairball. For some reason, though, complexity science types and physicists who dabble in complexity theory really like to use hairballs. You may have seen those like giant pictures of the internet in which they have rainbow colors all in that thing. It's a mess to interpret from a visual perspective, but it just looks kind of nice. So okay, I guess if that floats your boat, go for it. However, if you want to go rational with your visualization, there are a few options. The first thing that you can do is you can use a matrix to represent your graph data. And this flows naturally from that conversion that we can do between circles and lines that we draw in our mind to an actual structured two-dimensional matrix representation of a graph. So how do we interpret this? Well, the way we interpret this is as such. Every row is a node. Every column is also a node. You can order them in the exact same order. If self loops are allowed, that is, a node can be connected to itself, the diagonals may be filled, right? Because the diagonal is, the cells of the matrix are filled in, say, for example, 1 and 0. 1 for there is an edge between those two nodes, 0 for there is no edge. Or it could be weighted, so you'd have varying numbers, floating point numbers all over the matrix. You can even have negative numbers if you know how to interpret that in your own application. And so we can fill in the matrix according to whether there is an edge present or not. If self loops are allowed, then the diagonal may be filled. If self loops are not allowed, the diagonal of this matrix, I'm mousing over it here, that will be an empty cell. All right. So immediately from this graph, we can see that it looks like there are no self loops inside the graph, which sort of makes sense. You'd have a really narcissistic 7th grader to say, I like myself 3 times, right? So, okay, so this is one option for visualizing a network. Keep in mind that there is a natural matrix representation of a graph, and that will come in really handy with Notebook 6 on bipartite graphs, and there's some good applications there. We could, yes, exactly. Absolutely, absolutely. I chose to convert it to binary, but definitely you can definitely have a heat map style thing where really hot edges correspond, really hot squares correspond to, say, for example, in a transportation network, really hot edges would be really hot transportation activity between 2 nodes, for example, right? So that would be a good change to this plot. Okay, so the next one is the arc plot. I think I have it back here. At its core, the arc plot is drawn as such, in which we put all of the nodes on the x-axis or on the y-axis, and we draw arcs between them, all right, indicating relationships. And what's nice about this mode of visualization is we can now have a way of prioritizing the placement of the nodes over anything else. So we can prioritize the placement of nodes by, say, grouping them. Where are all the boys? Where are all the girls? Let's group them together and order them on the x-axis. And then now we draw edges between them. So now we can start to visualize what's the cross-group connectivity, the intra-group connectivity, and it's a much more rational way of visualizing this. If you constrained the placement, yes, but then now you're not doing a hairball. You're actually trying to find some rational placement of the edges. So basically, in my view, the principles behind rational graph visualization are find some way to group the nodes, to place the nodes on your Cartesian plane, find some rational way to do it by grouping, by ordering, and whatever, and make them correspond to one of the two axes that are on the Cartesian plane. And that will work really well. So you'll find that the arc plot is actually the basis of many other types of rational visualizations. For example, the Circos plot, right? So if you scroll down and you run that cell down there, you'll see the same graph now drawn as a Circos plot. Oh, question. Oh, the arc, sorry, my apologies. Arc plot was just made 2.5 hours ago, and I did not. Oh, you did? I must not have uploaded it just yet. Don't worry, everything will be pushed up to GitHub post-tutorial so you can pull it back down. Arc plots form the basis of all the other plots. Many other types of rational visualizations. So you can have a Circos plot over here. And if you observe the NXVis API, basically it's something like this. You instantiate the plot, you pass in the graph, and then you tell NXVis by what keywords you want to group or order the nodes, right? And it becomes a nice rational visualization that way. And so you can see that it's really just a transformation of the arc plot. Then after that, there's the Hive plot. The Hive plot is something that still needs to be implemented for NXVis. So I'm just going to show you the concept of it, but not the actual API, and I'm not going to run through this code here. The idea behind a Hive plot is as such. If you look at the screens, or if you look at your own screen, you'll notice we have the nodes grouped by some keyword, right? And so now we have the males on one side, the females on the other side. And then if we were only interested in intergroup connectivity, we'd look at this set of edges over here. On your screen, it should be on the left-hand side of the Hive plot. That would be the two group, so these represent the intergroup connectivity. And then if we're interested in the intra-group connectivity, what we do is we have a cloned axis. So this axis that I'm mousing over here is actually identical to this axis over there, and we simply draw the edges in between them. So it's a very nice alternative way of visualizing inter and intra-group connectivity. All right? Okay, so that's a whirlwind tour through the NetworkX API, plus hopefully my pitch to you as to why you should do rational graph visualizations. They are aesthetically pleasing. They help you with interpretation of the graphs. And basically, they're just not hairballs, all right? So I really detest hairballs. I have very strong opinions about this. Don't use hairballs wherever possible. Okay, so with that, let's see. How are we doing with time? 2:15, I'm told, is when Snacks' first call is. The first call for Snacks is. Alex, where are you? Are Snacks ready right now? I'm wondering if you could help me check that. Okay, thank you. If Snacks are not ready, we'll move on to Hubs and Paths, which is the challenging notebook. But if Snacks are ready, then I think this would be a good natural time to take a break. So we'll just wait on Alex for a little bit. In the meantime, are there any other questions so far about the material? At the moment, I think I want it to behave like a statistical graph visualization. So very few options are exposed. However, matplotlib is the underlying backend for NXVis. So if you're familiar with the matplotlib API, I've done this before with other packages, grab the axes object and start manipulating the axes object itself. So that's possible. Hypertree. Short answer is no, but I'd like to learn more. Okay. Snacks are ready. Okay, this is a good natural time to take a break. So we'll come back in, say, 5 to 10 minutes. Let's do 10 minutes. How are people doing? Feeling good so far? Feeling good? Okay. We're going to go into a really fun notebook. This notebook is notebook number 3. It's titled Hubs and Paths. So I'd like everybody to open up the student version of notebook 3, please. And then run that first cell, make sure everything runs fine. And before we go on, I'll have you load the data as well. So this one is called the project was called Sociopatterns. It is a network of people that passed through this infectious stay away exhibition in Ireland, I think, yes, in Dublin. So the nodes represent exhibition visitors, and the edges represent face-to-face contacts that were active for 20 seconds or more. So I was talking with you for 20 more seconds, then we have an edge between one another. And multiple edges between two nodes are possible and denote multiple contacts, but in this particular case, I've simplified the graph data such that there's only a single edge between a person and another person, and we don't encode this multiple edge type of data. It's a bit more complicated that way. All right, and so this network contains data from the day with the most interactions that happened, so it's nice and rich, and we can also explore things like the temporal structure of the edges and how they emerge, all right? So open this up, load the Sociopatterns network data, and check to see that you have 410 nodes connected by 2,765 edges, all right? So that data should all be correct. Okay. When you think about a disease network, a disease spreading network, some things start to come into mind. You want to find really important people in this disease spreading network for a good reason. Because you can catch them, isolate them, vaccinate them, stop them from spreading the disease, you can have a very good chance of stopping this disease from getting any worse in the population. So, and in another case, let's say we're not talking about disease spread, we're talking about information spread. We want to reach the maximum audience. Who are the people you go to? You'd want to go to pretty important people, I'm guessing. So the question then is, how do we evaluate how important people are conditioned on the network that they belong to? Okay? So, what are some thoughts? Let's say we're talking about a bit more lighthearted of an example, information spread on Twitter. Who are the people you want to go to? People with the most followers. And the reason being is, yes, pretty obvious. We want them, they're the ones who are able, they have what we would call a lot of people who are listening to them. They have a lot of neighbors in the network, right? Let's say this was in a company, and you wanted to, and you know that the company was connected by two people who shuffle, who are like gatekeepers to flow with, to info flow. You'd want, this is a weird company in that, like, yeah, it's not Slack, right? This is a weird company where there are two divisions and they're warring with each other inside, or competing with each other, but sometimes they also need to collaborate with each other. So there are two gatekeepers, the managers, basically. So you'd want to connect them. But the managers don't talk with people on the other teams. They only talk with themselves. Yet they would also be an important person that you'd want to connect with. Hold that example in your head. We'll come back to it in a moment. For now, let's think about the Twitter example. I mentioned neighbors. Neighbors is one particular metric that we can use to figure out who is an important person to look at inside this contact network. And neighbors are defined as anybody that I, a node, have an edge to. right? Any other node that's connected to me is my neighbor, right? So NetworkX provides a function, every graph object G provides a method called neighbors, and you can pass in the ID of a node. Note here, the node doesn't have to be an integer, it can be a string, right? So you can encode anything as a node, really. I can pass in the node ID, say node number 7, and get back the number of neighbors that that node has. So if I change this, so in this case, individual number 7 has 7 neighbors, individual number 8 has 12 neighbors, individual number 9 has 14 neighbors, okay? So knowing this piece of information, we can start to rank nodes in the network by how important they are, simply by how many neighbors they have. So I'd like you to attempt this exercise down here, which is to create a ranked list of the importance of each node by the number of neighbors that they have. Right, quick check. How are people doing? How many are done? Thumbs. Okay, we'll do a hard stop at 2:36. For those of you who are done and you want to move on to the next exercises, take a look at the rest of the notebook, please feel free to go ahead and do so. Question? So in this case, the directionality, if this were a directed graph, g.neighbors defaults to successors. So edges that come out of me and point to someone else. Those would be my neighbors. Predecessors are those that come before me and are pointing to me. So you would have to use, actually it's better if it was a directed graph, you would want to use the explicit terms successor and predecessor. Actually, let me just quickly check here. I don't remember whether I did this as a cast this as a directed or undirected graph. I cast this as an undirected graph. And that's because, oh, well, this is the nature of the data, right? So if we're in contact, then it's automatically reciprocal. Okay, so it's 2:36. I'm going to very quickly run through what I have over here. Essentially, we use the sorted function. We pass in the iterable. The iterable is g.nodes. We sort on some particular key, and this key in this case is the number of neighbors that it has. And I want it to be reversed, so we pass in reverse equals true. And here are the first 5 nodes. They should be in that order: 51, 272, 235, 195, 161, and so on. All right. So now there's an analogous metric called that's based off the number of neighbors that a node has, and this is called degree centrality. So degree centrality is implemented in NetworkX, and you can call it by doing nx.degree centrality. You pass in g. Actually, I'm going to build this up bit by bit for you guys. So let me take all of this, comment that. Ooh. There we go. Copy, paste. If I do nx.degree centrality and I pass in a graph G, what we will get back is a dictionary. The keys are the nodes, and the values are their degree centrality score. So degree centrality, actually I should have backed up. Degree centrality is defined as the number of nodes that I have divided by the number of nodes that I could possibly have. It's a very simple metric. Now there is one little thing that you have to note. What's the number of possible nodes that I could have if self loops are not allowed? N minus 1. So if I have n nodes in the graph, n minus 1 is my denominator if self loops are not allowed. And if self loops are allowed, then it's n at the bottom. So this depends again on how we define what the graph is. So in this case, the question is, if I have 2 subgraphs that are completely disconnected from one another, how do we calculate the degree centrality metric? In this case, you'd have to first start with the definition of the graph. It's the node set and the edge list set. If the node set encompasses both subgraphs, then the total number of possible nodes that I could have possibly been connected to is all of the nodes in both clusters minus myself if self loops are not allowed. So it goes back to the definition of how we define the graph. If the graph itself is, if we're talking about a subgraph on its own being the graph, that's a different story. All right? Okay, so we get that, and we can get the degree centrality scores by calling on nx.degree centrality, passing in g, and if we cast this as a list, we can get back all of the degree centrality scores as 2 tuples in this fashion. All right? People okay with that? Now, if we inspect the dictionary, the original dictionary, nx.degree centrality of G, you'll find node 51 is the one that has the highest degree centrality, and we can check that by, again, checking the metric, and you can even hand calculate this for yourself. Okay, so what I'd like you to do is to embark on a few exercises that are designed to get you familiar with this concept of distribution of metrics on a graph. So when people here are familiar with probability distribution, I'm assuming, is that correct to say? So a probability distribution means you can take a range of values and there are different likelihoods associated with each value. In a graph, you can have, say, a degree centrality distribution or a neighbor distribution, which is the distribution of number of neighbors that each node has. So what I'd like you to do is to get familiar with this concept for graph setting. How many of you are familiar with what we call an ECDF? Okay, very few. How many know what histograms are? Okay, everybody. I predicted that. There is a relationship between a histogram and a CDF, or the ECDF. The ECDF is essentially the integral of the histogram, but better, right? Because, I'm sorry, I'm a little bit opinionated on this one as well, because I was recently converted in last year, November, to start dealing with CDFs and not with histograms, for a few reasons. The first one, with histograms, you can hide and obscure data simply by changing the binning width of your histograms. It's a good way of cheating people. So don't do histograms and don't manipulate your histograms to cheat people. All right? That's a problem with histograms, and that's the biggest one. If you do the CDF, you're plotting every single data point. You're not binning anything. And so then you'll get a better feel for what the data actually looks like underneath the hood. So this bimodality, for example, could have been obscured simply by changing my binning width. Whereas the bimodality doesn't get obscured by plotting all of the data points and plotting their cumulative distribution from 0 to 1. All right? The other nice thing about a CDF or an ECDF is we can easily read off quantiles or very important percentiles, the interquartile range, the median, the 95th percentile, the 5th percentile. All of that is readily available from the CDF. So I'd like you to do that. I have, I believe, imported ECDF as a function for you all. I don't want you to worry about the underlying implementation. So just go ahead, use that function. And then you can, just use that function. Don't worry about things. So go ahead and try creating an ECDF of the distribution of degree centralities, the number of neighbors, and the scatter plot of centrality against number of neighbors, just to validate and verify for yourself that they're derived from the same number. No, I don't have an opinion on density plots yet. If any of the API calls are tripping you up, I'm flashing up my answer on the screen so you can reference it. The part that might not have been clear, I should have mentioned this earlier, is you can do ECDF and it returns 2 items together. So you can do the tuple decomposition inline there. So xy equals ECDF and you pass in some iterable of numbers, basically. Nope, we magically do it inside the ECDF function. Okay, so how many people are done with plot 3, the third one where you have like a straight line? All right, we'll continue waiting for people, probably do a hard stop at 2:49. But then don't feel pressured. In this particular case, don't feel pressured to finish the exercise. The more important part here is the concept that we're trying to convey. Okay, so it's 2:49. We'll do a hard stop. You all will have access to the answers, so don't worry so much about the exact implementation. Basically, what I wanted you to get to was this straight line. Number of neighbors is directly related to the degree centrality by that math formula, so there should be no question about this. Now, though, I want you to keep in mind this plot because degree centrality and another metric of centrality are not necessarily correlated, but they're both measures of importance of a node in a graph, and so I'd like you to, again, keep this one in mind. It's an important thing to put in your back pocket. All right, we're going to look at do a very quick exercise on visualization with NXViz, and personally, I like Circos plots the most because of the richness of information that you can encode in a compact space. So what I'm going to have you to do is to instantiate and draw a Circos plot for this graph. And we want them to be ordered by the order of nodes that they come in. and colored by their order as well, right? And so I've provided for you on-the-spot docs because NXViz doesn't have docs right now, and that's my fault. But on-the-spot docs are provided, so go ahead and give that exercise a shot. It's not the Eye of Sauron, though. Well, actually, thankfully, it's not the Eye of Sauron. And quick check, how many of you are done with this one? Okay, we'll do a hard stop at 52, 53. So it's 52. Let's keep the pace going. Part of why I wanted you to do this exercise is just to highlight what a declarative API is. Mine is not. NXViz's declarative API was actually inspired by Altair's declarative API, which is also, and a few others. Like Bokeh has its own declarative API for how you plot things, which is basically you tell what you want plotted and not how you plot it. And so I want nodes to be ordered by order, the keyword order, and I want them to be colored by the values keyed on order. And I don't want to tell NXViz how to color each node. I don't want to specify the color map. I'll provide you with nice defaults that maybe you can change later on if you're so inclined. All right, so that's the basic idea here. And you should get something that looks like that. And actually what's important here is let's do a bit of interpretation on this, right? Let's do a bit of interpretation on this aesthetically pleasing visual. What do people think is going on over here? So remembering the context, what's going on over here? Yep. Anything else you see? Yeah, basically that's what I would have seen. Are there any other alternative interpretations? Not that I can think of either myself. So basically, this tells you I'm only going to interact with people who are close to me in order. Now, if I had ordered them by time, then we'd actual time and not just order, then yes, we would have even richer information. But unfortunately, I don't have that data, so we can't do that. So here's the alternative. We do it by order. This is where the start is, where my mouse cursor is, and we go around the circle. Some people apparently stayed a long time, or stayed long enough that they could interact with people who were far away in terms of the order that they came in, right? So, and if order is a proxy for time, then then we can probably claim that they stayed for quite a bit of time. Okay, so let's talk then about, let's take a little bit of a detour from this notion of neighbors, because when we talk about a graph, there's also one more thing that's really important, that's paths in a graph. Paths in a graph, pathfinding, is very important to our daily lives. Otherwise, we'd never be able to get around town, right? On our cars or on our bikes. Or pathfinding is very important because that's how we navigate a graph. And if the graph happens to be Google Maps, then that's how we navigate our local home city. Okay, so now with paths in other types of networks, so for example, in a social network, we might be interested in information spread, right? And information spread can happen through what we had just learned about, which is broadcasters, people who have really large reaches immediate to themselves, but they can also be spread through other mechanisms, and those other mechanisms might thus involve people that are like bottlenecks in the transmission chain of information. Those are the ones who are really important, because without those bottleneck people, we wouldn't be able to get information to other communities, right? So these gatekeeper people or these bridge people between isolated communities. So one thing that we might want to look for a graph, in a graph, is what's the shortest path between two nodes? What's the most efficient way to get a message from me to someone else, right? So let's think through this. There are multiple approaches to solving this problem. I'm not going to claim to be an expert computer scientist and explain all of the algorithms to you. Rather, I want to give you a flavor for the concept. So we're going to go through the breadth first search algorithm. People here probably have heard of the breadth first search algorithm, right? Raise your hand if you have. Okay, if you haven't, just like Alan Downey, I like to refer to Wikipedia for good explanations of stuff that aren't colored by politics. So the breadth first search is not going to be colored by politics, and so we can have a pretty objective explanation of what that is. And the approach essentially is as such, right? We start with a queue, and that queue has like a node, and then we go check the neighbors 1 degree out, and then we go over each of the neighbors and look for their neighbors, and we ask, as we're searching through all of these neighbors in turn, is my destination, have I reached, will one of those neighbors be my destination node? And once we hit that destination node, we can like kill the algorithm and say, this is the path that I need to go through. Okay, so what I'd like you to do is to try implementing this function for a graph. Now, if you need a toy graph to anchor your thoughts, feel free to use this graph over here. Otherwise, if you want to operate on the real graph for this exercise, you can do so as well. There's pen and paper up at the front if you need to like scribble so that you can implement the algorithm. But I'd like you to actually try implementing this within the next, implementing this algorithm in a function called pathExists. It doesn't tell you what the actual shortest path is. It just asks, is there a path between these two nodes? And we figure that out through the breadth first search algorithm. So yes, like I was mentioning, if you want to use a toy graph to anchor your thoughts, you can use this. There's pen and paper up front. Otherwise, go ahead, give it a shot. Could not solve this without pen and paper. think it was a vestige of something else. Thanks, Dan. For those of you who might need a hint, in this toy graph over here, there's something that we're doing where we're checking every node and then going down that node list and just keep checking on what other nodes are, what other nodes we need to check their neighbors for, and we always make sure we never add in a node that has already been visited inside the graph, and that's a very important thing to do, otherwise you might end up in these infinite loops where Apple is. So yeah, make sure you need something like that to happen. My own implementation, which I'm flashing up here for those who truly feel stuck, you can go reference this, that's no problem. There's this thing where I keep track of which nodes have been visited, and so we use that as a filter for how we add nodes to the queue, all right? Did I get your GitHub username right? Yes. Okay, quick check. How many of you are done with this problem? Okay, this has been faster than most other sessions that I've been through. So for this particular problem, I'll give probably 2 or 3 more minutes. It's like the previous one, not one that I expect people to be able to finish, but because it's the nature of it, it's a bit more challenging than usual. The main idea is you're able to think through a graph problem. The time constraints are kind of artificial. In reality, I took about half a day to figure this out for myself and be convinced of my own solution. And even then, I still had bugs pointed out by other people. So I'm not expecting everybody to be computer science whizzes and have bug-free code the first time around. Okay, so in the interest of time, I'm gonna have people stop coding at this point. I'll very quickly, very briefly talk you through what the algorithm looks like. Um, and basically, we have to pretend we're the computer. We know nothing about the entire structure of the graph. So we start here at this position x, and we want to make our way to y and check whether there is a path between them. So the breadth first search algorithm says, let me look at x's neighbors. X's neighbors include A. So sorry, that's where I am, the blue dot. Everybody can see that, right? With the blue dot. We start at X, we move to A. Let's append A to this Q, because that's now the next thing. Sorry, we started at X and we found A. So let's append A to this Q. Then we're at A now, and we look at A's neighbors, and there are B and D. So let's add B and D to the Q, and now let's move on to the next node in the queue, which is B. So now we're at B, and who are B's neighbors? A and C, yes, that's right. But we don't add A back into the list because we've already visited A. So we're keeping track of the fact that we've already visited A, and so we only add C, append C after D. Now we go down to the next node in the list, which is D, and we ask who are the neighbors of D? A, E, and Y. So we actually have 3 neighbors, and once again, we have to check. We don't want to add A back into the list, so we only add E and Y. Now, at each check, we're also checking, is my neighbors, however many neighbors, does that include the destination node? In this case, Y is the destination node. So at this point, when we ask, who are the neighbors of D? We have A, E, and Y. We don't add A. We check then, is E the destination node? No. Is Y the destination node? Yes. Break the code. Stop there. We found a path. We don't need to continue iterating anymore. So we never even check C and E we never check their neighbors. All right? That's the core of the algorithm, and this is sort of like how you think through networks. For me, this was like the enlightenment moment for myself in my network journey, where I realized, okay, as long as I think through the network node by node, neighbor by neighbor, I can probably solve the majority of problems that I'll ever encounter with network analysis. Right? And so that was the big eye-opening moment. Okay, so if you were smart, you would have done recursion. I'm not smart, so I didn't do recursion. But recursion is I know how to do it recursively. I just think it's not as explicit as doing it in a non-recursive fashion. So non-recursive is like easier to understand. Okay, let's see. Now NetworkX. Now for those of you who actually successfully implemented the algorithm, you didn't have to, because NetworkX has a shortest path algorithm, which you can actually query for a Boolean, which you can turn into a Boolean query as well, true or false, simply by looking at whether it's an empty list that's returned or whether there are elements in that list of nodes that give you the path. So if you do nx. So by the way, for the record, this was the only time in the tutorial where I asked you to implement something that's already implemented in NetworkX. You will not have to do this again this tutorial. It's all right. So shortest path, you can pass in the graph G and the 2 nodes for which you want to figure out whether there is a shortest path or not. So in this case, node 4 and node 400. And what we get back here is a list that starts at 4, ends at 400, and it just so happens that's the exact order you would have to traverse to get from 4 to 400. All right? Underneath the hood, I'm not sure. Probably a variation of that one, the Dijkstra's algorithm. Okay, but if you're really curious, the docs have all the answers for that, the NetworkX docs. Okay, so from this point onwards, all the code that we write are just going to build on top of NetworkX's functions. So you can write higher order queries, try to write these other queries on the graph that will help you understand the local structure of the graph, all those sorts of things. So here's an exercise which I think is a useful one to have, which is to extract the edges that are returned, extract the actual edge, the set of edges between for the shortest path between two nodes, and then draw them onto screen using the nx.draw function. So why would you want to do this? Well, it's one thing to say, this is how these are the nodes in order. It's another thing to say, I'll draw it to screen, and if I have the capability, I might also not just draw that set of nodes, which is this exercise. I might want to build on top of this exercise and say, let me draw that set of nodes plus all the nodes 1 degree off from the path nodes inside that path, right? And that's a perfectly valid thing to try. So I'd like you to try this, which is like the base code. There's a hint over there. You can use g.subgraph, which takes in an iterable of nodes, and you know how nx.shortestPath works as well now. So now give that a shot. Okay, quick check. How many people are done with this exercise? All right, I think we can move on then. You should get something that looks like this. So we're now, basically you can see we're composing NetworkX's elementary function into higher order things that are of interest for ourselves. So we can use the hasPath function, or in fact, we could even omit that, right? You could say if nx.shortestPath is an empty list, then oh wait, no. I think if nx.shortestPath, if there's no shortest path, it will error out. So that's why I had to do nx.hasPath first, and then nx.shortestPath is a callable thing that will not error, guaranteed not to error out under this condition, right? And yes. Over here. I've been reticent to use NX's nx.draw, so I'm actually not very sure. I think that's something to check in the docs. I think you can have the thickness varying by the values that are on the edge. I think that's possible. Yes, the layout is arbitrary. So oh, they do. For let me see. You don't have 490, 111, 112 for your shortest path? Okay, that's actually a good point. There might be multiple. I forgot to mention this. Thanks for pointing this out. There may be multiple shortest paths between two nodes, and in the case of NetworkX, it will just return one of them. Probably. Yep. So under the hood, you're guaranteed to get a shortest path. You're not guaranteed to get all of the shortest paths. All right? Okay, so you should get something that looks like this. It's a useful function to have in your back pocket, and it's useful, again, to know how to do the software engineering to compose functions together. All right, so what we're going to do is we're going to skip past the challenge exercises that I'd like to invite you to do it at home. I'd like you to come back, scroll all the way down to section 4, or this section, sorry, you don't have the numbers on your notebooks, to the section called Hubs Revisited. All right? So now, so this comes back to the point that I was trying to convey just now, which is sometimes you've got to have messages passed between communities, and there are gatekeepers to the communities. Now, these gatekeepers don't necessarily have the highest degree centrality, but a lot of paths have to pass through them in order to get messages between the two communities. So they would have what we would call a high betweenness centrality. And so this high betweenness centrality, this betweenness centrality metric is, if I'm not mistaken, it's defined as the number of shortest paths that flow through a particular node divided by the total number of shortest paths that exist in the graph. It's a bit of a thing to wrap your head around. The number of shortest paths that flow through a particular node divided by the total number of shortest paths that exist in the graph. Okay, so that's the betweenness centrality metric. And if you plot the betweenness centralities against degree centralities, that's when you might be convinced that betweenness centrality and degree centrality don't necessarily follow a linear relationship. So I'd like you to attempt that exercise below. I'm not going to show the answers just yet. So give yourselves a few minutes, make that scatter plot. Quick check thumbs if you're done. few people. Go to 323 or 324. Bless you. All right, quick thumbs who's done with this one. All right. Again, in the interest of time, don't worry about the specific implementation. You can always take a look at the instructor notebooks and get the code. I just wanted to show, indeed, for a given node, it's not necessarily true that something that has high degree centrality would have high betweenness centrality. They're somewhat, but not really well correlated. Okay? So now, I think I've given the answer away just now, but can you think about a scenario where you would have, or can you think about the structure of a graph, really, where you would have where you would have nodes that have low degree centrality but really high betweenness centrality? Sorry, can you say that one more time, please? So there's a cluster of people here and a cluster of people there, and that one person is in both of them. So they don't have a lot of neighbors in each of those. So I was asking, sorry. I think you were answering the reverse. Yes. Yeah. Yeah. So that's what we would call. There's a technical term for that. And I think we call that the barbell graph. This is like a barbell. There are two what we would call cliques, and there's a technical definition for the term clique. We'll get to that in the next notebook. So we have two cliques, one over here and one down there, and they're connected by a bridge. And so this guy over here has a degree of 2, but that person's degree centrality would be really, really high relative to the other nodes because lots of messages have to pass through that individual in order to cross the two cliques, right? So that's an example. And I think there's a bit of a life lesson over here. Humans are really fixated on metrics. Data scientists particularly. We love to optimize for one metric of importance, but in this case we saw there are two. There are two ways to evaluate the importance of an individual in a network. And I just hope we don't get caught up on evaluating people on single metrics. That's all. All right. Okay. Looking at the time, I think this is another natural break spot. So I'm going to let everybody go. Let's go for a 10-minute break. We'll come back here at 3:35. So we went through a notebook on hubs, paths, basically finding out what are important nodes, and I'd like to leverage some of that information, some of that new knowledge that we have now to think about other interesting problems on graphs. This time around in this notebook, which is notebook number 4, we'll be talking about structures, all right? So let's start first by loading some network data. So I'd like everybody to open up notebook number 4, student version, and we'll load some data. In this case, it's going to be a different network. This is a trust network. So it's like a social trust kind of thing. It's a network of physicians from 4 different towns. This was, I think, collected in the year 1966. There are 246 physicians, and a node between 2 physicians indicates, an edge between 2 physicians indicates that the physician on the left trusts the physician on the right for medical advice, right? Now, because of the nature of this chapter, or of this notebook, I've intentionally made the graph undirected rather than a directed graph, so we're assuming bidirectional reciprocity, even though this is not necessarily the ground truth in the underlying graph, all right? For their patients, Okay, so we'll load the data, and let's just make a very quick Circos plot of the graph. I believe that cell should be loaded inside your notebooks. And let's take a look at this graph over here. And very quickly, let's do a bit of interpretation. What do you see about this graph? It's separated. So how many separated groups are there? Roughly 4 of them. My hypothesis is they're basically grouped by the towns, right? In Illinois. So, and this being 1966, it makes a perfect amount of sense. If this was 2011 or 2017, maybe not, right? Physicians can talk with each other by Slack. No. They'd be really distracted. Okay, so let's talk about structures in a graph. There are some very important structures, and we're going to build from the most fundamental of them to these really large structures that we can look for. And the first one I want to talk about is called a clique. All right, so a clique is a set of nodes in which every individual is connected to every other individual. So what is the simplest clique that exists? Nope, not family. 2 nodes connected by an edge. That is the simplest clique that you can have in a graph. Sorry, I was not thinking social. I was thinking like graph theoretic cliques. My bad. I should have clarified that. So then what is the simplest complex clique? It's a triangle. I've drawn this up here. So triangles, and if I remember correctly, the pure mathematicians have another term for this. It's called a simplex or simplices. And I can never get my head straight about whether a 2 simplex has 2 nodes or 1 node, but basically there's an alternative term called simplexes. And if you read about it in the combinatorics and graph theory literature, don't be surprised by that term. It's basically cliques. It's cliques of some size, basically. All right? All right. So triangles are a very interesting structure, and for a variety of reasons, in that it's, 1, the simplest complex clique, 2, if we want to fill in triangles in a graph, that corresponds to some really lucrative data product that was built by LinkedIn called the Friend Recommender System. So we'll look at that as well. But first, let's start with the basics. Let's start with the basics by looking at whether a node exists inside a triangle or not. So a simple algorithm for doing this would be, let me look at a given node and check its 2 neighbors, check 2 of its neighbors, sorry. And if 2 of its neighbors have an edge to one another, then that is a triangle relationship. Thankfully, we're not talking about romantic ones. We're talking about graph theoretic relationships. Triangles are good. And the code, sorry, the puns get really good at this point. It has been a long day. So if you look at the example code inside the instructor notebook, I believe it's also in your student notebooks, you'll see something that looks like this. We first assume that a node is not in a triangle. That's this line over here. And then we iterate over every pair of a node's neighbors. By definition, there's an edge there. And then we just ask, is there an edge between those 2 nodes? And if there is one, then we say, yes, it is in a triangle relationship. Otherwise, no. OK, so with that, now, we don't necessarily have to implement this on our own to know whether there is a triangle, whether a node is existing inside a triangle or not, because NetworkX has an nx.triangles function. And what that will look for is it'll return the number of triangles. that are present. So by definition, you get the Boolean stuff for free. If it's 0, it's not, and if it's anything but 0, it is. So what I want you to do is now let's continue this exercise where we're building on top of NetworkX's functions. So let's look at this exercise over here, in which what I'm asking you to do is to take in one node and its associated graph, and return a list or set of itself plus all the other nodes that it's involved in a triangle relationship with. Right? So let me actually make this a bit more clear. If I ask you for this node over here, if this node is the input and that is the graph, I want you to return a list that includes this, and that. Right? So you return the list of neighbors that are also triangles with that particular node. All right? That okay? The prompt clear? If there are any questions, ask me during this time. So go ahead, give it a shot. That's right. We don't need to know, the requirements for this function is basically just give the list of that node plus all of the neighbors that are in triangle relationships with that node. Quick thumbs, quick check. Thumbs if you've reached the plotting portion. All right, just a few for now. We'll go till 47, 347. And for those who feel extremely stuck, don't forget there's the instructor notebooks to reference. I'm also showing the answer on the screen. Okay, so we're gonna do a quick hard stop on the exercise. In the interest of time, I'm gonna talk you through what my implementation was, just so that you have a feel for it. So the key to this implementation is to look at to use the combinations function from the Python standard library itertools module. What the combination function does is it accepts two parameters. It accepts an iterable and a k. So this is of how much size do you want to iterate. So what it'll do is it'll return every pair without repeating, right? So that's how we can check conveniently without writing a double for loop and all this check for if this equal, not equal that sort of thing. Then the other part of it is we use g.hasEdge to check whether there is an edge. And of course, at the end, we're simply keeping track of the triangle nodes. So that's the requirement of the function. And so we'll add neighbor 1 and neighbor 2 if it fulfills this criteria. So we should get something that looks like this. And indeed, you'll notice each of these other nodes, 67, 42, 11, 9, and 41, they exist in a triangle relationship with node number 3, even though they're not in triangle relationships with, you don't see like 3, 41, and 11, for example, as being a triangle. But that's okay. This is sort of what we were getting at. And this is an example, again, of where we can use nx.draw to draw subselections of the larger graph to get a feel for the local structure of the network. Okay? You can also compare for yourself that those nodes, which are neighbors of node number 3, they are the only ones that are in triangle relationships with node number 3. Other nodes like 112, 101, 91, and 1, they're not in a triangle relationship, but they are neighbors of node number 3. All right? So this is something that you can use to check for, to look for triangles and grab them out and visualize their local structure. So it might be useful, for example, if you were exploring a social network of sorts. So there's this, I alluded to it just now, there's this problem of open triangles. The recommendation system that LinkedIn built is basically founded on what they called triadic closure. An open triangle looks something like that. Some people say it's just a line. I mean, yeah, sure. But yeah, topologically they're identical. But an open triangle is a useful thing to look for because if this is individual A, that's individual B, and that's individual C. If A knows B and A knows C, then there's some probability that B also knows C, and our evidence can get bolstered if we also observe that, and we observe that, right? So we've got so many open triangles there, why aren't B and C connected to one another? So this is an example of where, oh yeah, open triangles, an interesting thing to find. So now what I'd like you to try is to look for open triangles in a graph for every node such that, sorry. What I'd like you to look for now is open triangles, nodes that are involved in an open triangle relationship. This time though, I'd only like you to consider the case where the node is the center node and not the edge nodes. That's a bad term. Not the peripheral nodes. The edge nodes is kind of confusing in a graph sense. So they're not the peripheral nodes, they are the center node. Do people get it? No. Okay. All right. Let me illustrate this. I can be in a triangle relationship this way, where I'm talking about this node. That's the center node of the open triangle. I want you to look for nodes in the middle that are in an open relationship, because it's a slightly different algorithm to find the open triangles for nodes that are at the periphery of an open triangle. All right, so it's slightly different. I want you to just implement this case. All right, so this should be analogous to looking for triangles in a different way. example, if you have a scenario like this, that is an example that's sufficiently complicated, but also sufficiently simple. So if you have a scenario like this node is in an open triangle relationship with this guy and this guy. This node is also in an open triangle relationship with this guy and that guy. I want to return this triplet and this triplet, all right? Do a list of 3 tuples. Okay, so in this case, we would do, I'll probably reorder the prompt a little bit. So return A, B, C, comma, B, C, D, and that should be it. Right, so return the list of 3 tuples, or a list of lists if you want, it doesn't really matter. Question? Doesn't matter. Quick check, how many people are done? Okay, we'll wait for about 60% quorum to move on. For those of you who are done, feel free to move on. Is there a question? David? Part? Oh, the plots. Oh, you tried, yeah, okay, yeah, the plots take some time. I actually don't recommend trying to plot it. It gets really messy. Okay, so just want to check how many people have 33 open triangles for node number 3. That's right. Those are 33 open triangles that it's involved in. So like I was mentioning, it's the core idea behind these social network friend recommendation systems. And really, that's the core of it. If you think through the problem in a network fashion, then that's how we get to it. All right, so we figured out how to find triangles. And triangles are the simplest complex clique. And so now let's find out what cliques are actually present inside the graph. So first off, cliques, let's recap. What's the definition of a clique? Popcorn style? We have popcorn? Exactly. So within that clique, every node is connected to every single other node. In the absence of node E, this is a clique. With node E, if there was a connection over here, this whole set would not be a clique. There's this concept called the maximal clique. In this case, A, B, C, D form a maximal clique within this graph, A, B, C, D, E. All right? So a maximal clique is actually defined as I cannot add any more nodes to the clique and still be a clique. All right? I cannot add any more nodes to the clique and still be a clique. Therefore, I am a maximal clique. All right? And NetworkX actually has a maximal clique finding algorithm. It's called find cliques, and it will return all cliques from size 2 to size whatever. Two dimensions. What do you mean? How? If that happened, then yes, we have a maximal clique, a new maximal clique. Sorry, you were in Cartesian dimensions. Okay, my bad. I was not in Cartesian land at that point. And I don't know which land I was in. Clearly, I physically exist in the Cartesian plane. Okay, sorry, my bad. Yes. So if E were connected to all of those 4 nodes, then yes, we would be allowed to call that a clique. But if E was not, then we can't. All right? So that's the definition of a maximal. Then ABCDE would not be a maximal clique. ABCD would be. All right? Okay. So NetworkX has the find cliques function. You'll notice it returns cliques of all sorts of sizes, and it returns 2, size 2, because an edge is a clique by definition. So every edge inside the graph is a clique of itself. But it may not necessarily be a maximal clique. If that edge is embedded inside a larger clique, then there's a larger maximal clique that's inside there. This kind of gives rise to a neat property, right? So every clique can be decomposed into edges. That's a trivial conclusion. Actually, every maximal clique, I think, can also be decomposed to triangles. So for example, if I just had this case, ABCD, without the extraneous E connections, I can find 4 triangles inside here, right? So I can find, the triangles would be, yeah, it'd basically be, so if this is a maximal clique of size k, it's k choose 3 for the number of triangles that exist inside there. So I have ABC, ABD, BCD, and then CAD, I think, right? Those are the 4 triangles inside the larger maximal clique. So it's a neat thing. I don't know exactly what I would use this for, but it's a neat property to realize. So one thing that we might be interested in though is we might be interested in, say, maximal cliques of a given size. Say we're doing a social network and we want to look at all 4 cliques and 5 cliques and 6 cliques and see whether there are different properties to the sizes of each of these cliques. So we might want to do a search for this. So what I'd like you to try is to check, well, I flashed the answer, whoops. Write a function, sorry, here we go. Write a function that takes in, called maximal cliques of size, and it takes in 2 parameters. It takes in the size parameter and the G parameter, and it returns so it's basically filtering at find cliques for cliques of a certain size. So give that a shot. Don't spend too long on it. The key idea, again, is get familiar with composing functions. Okay, quick check who's done with this exercise. All right, we'll go 1 more minute. Do a hard stop at 4:03. right. I'll very quickly talk you through my own implementation. There are two defensive programming checks. We want to make sure that the size parameter is always equal to or greater than 2. There's no such thing as a maximal clique of size 1. And the other part is we only want integers, right? These are discrete objects, so we never deal with continuous floating point numbers. Okay, so you should have something like this. It's just a list comprehension, and it filters. It's a list comprehension that you would do to filter out a large iterable based on some criteria. All right, the final part here moves from cliques to somewhat larger structures inside a graph, which is what we would call a connected component subgraph, right? So a connected component subgraph conceptually looks like this. I think someone else just mentioned it before. We have two communities. They're not connected to one another, but we consider them as being part of this one large graph, right? And so each of those subgraphs is considered a connected component subgraph. It is a component of the larger graph. It is a subgraph, and they're all connected with one another somehow. It's not necessarily a clique relationship, but I can always find one path from one node to another node within that little subgraph. And there's no path from this subgraph to that other subgraph. Right? That's the definition of a connected component subgraph. So NetworkX has a function called connected component subgraphs. It takes in a parameter g, and it returns an iterator, a generator function that returns graph objects representing subgraphs, and these are the nodes that follow that definition of a connected component subgraph. So in this case, as everybody had predicted earlier, there are basically 4 connected component subgraphs inside the larger graph, and they probably, like we intuited, probably follow the town distribution of these physicians. So what I'd like you to do is now try a little exercise that involves some Python gymnastics. And I'd like you to draw a circos plot of the graph, but now this time coloring and ordering the nodes by their connected component subgraphs. So you might have to do some things where you have to annotate in the original graph what subgraph that particular node came from in the as returned from the connected component subgraphs. So you have to do a bit of Python gymnastics to link these two things together. So give that a shot. To modify a node in memory, you would do the dictionary select. Sorry, let me repeat the question. The question is, I think the question behind it is, how do you modify the node, right? So the way you modify it is you do something like g.node, and then you select that node, and then you set the attribute, the key value pair for that one. So I'm going to show you something like this. It would be g.node in subgraph equals 1 or equals 2. And now you have an attribute on that original graph G with that says that this node belonged to the subgraph number 2 as indicated by the connected component subgraphs. Right, this is the Python gymnastics that we have to do to get around that. Okay? All right, so do people have something like this? So those of you who do, give me a thumbs up. All right, for those of you who are still working through it, I'll give you a little bit of time. Let's do another minute, and I'll flash up the annotation code so that you don't get too stuck on it. Right? This is what the annotation code looks like. I'll move it up. Okay, I'm going to very quickly talk through the annotation code. So what we're doing is we're annotating on the original graph, the connected component subgraph that it belongs to. Now, a graph object itself doesn't have a unique ID, so we can create a unique ID for these subgraphs by enumerating over them. So subgraph 0 gets I equals, so for I, G, and enumerate CC subgraphs, we'll give the value 0 to the first subgraph, the value 1 to the second, and 3, and so on until we get 3 for the last subgraph out of 4 of them, right? So the small g is the object that we're iterating over. We iterate over each of the nodes inside the small subgraph. We can take advantage of the fact that that node n in the small subgraph has the exact same value as the node in the larger original subgraph. And so now we can annotate it. We can annotate the larger subgraph big G, not little g. We can annotate the big G with the subgraph that it is, that it belongs to. And so then we can color them by subgraph, and NXViz will color them according to some color scheme. And we can order them also by their subgraph, or group them by their subgraph, and we get back something like this. Question?
Yes. So the solid connected component means every node that solid connected component connects to every other node. There's a path.
There's a path, exactly.
That means that between the yellow group and the orange group, there's nobody that has a connection in the yellow group that has a connection to anybody in the orange group.
That's right. Absolutely. They're topologically separated. There's no way to get from one graph to the other by traversing edges. You have to warp space-time at that point. Okay. One thing that becomes kind of worrying is whether the US Congress will become two connected component subgraphs, or if the Canadian Parliament will become 4 connected component subgraphs. That's not a really good thing. I'm from Canada, so that's why I'm concerned more about the Canadian Parliament than the US Congress. But yes, we don't want this to happen, and so for those who are US citizens, please do something. We don't want the world to fall apart because two parties are fighting like nothing. All right, this is a fact. This is something that someone measured. I think I grabbed this from the New York Times. They looked at the number of co-authored bills between individuals of the same party, between individuals, and then labeled in what the party affiliation was. Democrats blue, Republicans red. So you can see very clearly the US Congress, how it's evolved over the years from bipartisanship to partisanship, basically. All right. Okay, enough politics for the afternoon. Let's move on now to notebook number 5. Notebook number 5 is going to be much more relaxing in that I'm going to do most of the talking for this one. You don't have to do much coding over here. This notebook is basically all about how do you store network data on disk. So thus far, you've all been given network data, and there's this magical object called G that you operate on, right? It's G dot something. So now how do we get to G? There are a few ways. I want to show you 2 ways which I think are useful. And one way is both are useful. one is not human readable but really convenient. The other is human readable, but you need a bit more effort to get to G from that original data. So the first one is storing your network data as a table. But actually, you can't store it as one table. You need two tables. So remember, a graph can be described as a set of nodes with their metadata and a set of edges with their metadata. This means in order to store the node and the edge data, you need a node list. And in order to store the edges and their metadata, you need an edge list. And that's what I've drawn up here. If you look at the whiteboard, it's basically like that. One file to store the node information plus their metadata, the other to store the edges and their metadata. If it's stored as a table, it means it probably is a CSV file. And for those of you who are here at Dan Chen's pandas tutorial, which is the morning session, you're in luck because we're going to play with pandas here. Now, for those of you who aren't familiar with pandas or haven't had much experience, don't worry. I'll talk you through the code. So first off, I would like you to run this block of code that checks for the Divi data set. So Divi is a bike sharing network in the city of Chicago. Boston has its own, which is Hub Bike, and I believe San Francisco is getting electric-powered bike sharing in the Bay Area pretty soon. It's a pretty sweet deal. They're like recently expanded, so it's really, really nice. Bike sharing is a new thing. So if this is a bike sharing data set, what would you imagine would be the natural nodes and what would be the natural edges for this data set? Popcorn style. Sorry? Origin destination would be the edges, and the nodes would be the bike stations themselves, right? So that would be a natural thing. And so what we've got is we've got trip data. We have individual riders, and they've taken trips between stations. And so a natural representation is we can ask how many trips were taken from one station to the other, right? By aggregating over all of this trips data set. So we can have a node list, which is the stations data set. And the stations data set would look something like this. If you run that code, you should see a table that, run that cell, you should see something that looks like this. You can get the first 10 rows. It's pretty clear how we're storing it. The ID is the node, so 5, 13, 14, 15, etc. And it's got a whole bunch of metadata. The name is State Street and Harrison Street. The latitude is whatever. The longitude is whatever. It's got some capacity for bikes. And it's got some landmark ID that's nearby it, and it came online at some particular date in time, right? So that's a natural representation for how we would store node list data as, say, a pandas as a CSV file. So right, in this case, we only have the capacity. We can't infer at any given time exactly how many bikes were present, but we can do the deltas, for example. We can ask how many were added or decreased over a certain period of time. So then we can also do the trips data set. So if you run this cell, it might take a little while for some people. Don't worry about it. Basically, when it finishes loading, you'll notice that the most important, the edge list, the edge information is stored as from station ID and to station ID. This implies that this is a directed network. Everybody agree with that, right? Now there's also redundancy in the information that was stored. So we have from station name to station name. We actually could cross-reference this back in the stations table, so we don't really need that. But there's also some other things. So for example, we have the time, the start time and the stop time. We have the trip duration in seconds. We have the bike, the exact bike that was used to ride. So that this is all metadata that is encoded for the particular ride, for that particular edge that goes between two nodes. I think at this point it's an appropriate time to introduce another type of graph that NetworkX offers, which is what we would call a multi-graph or a multi-directed graph. And this allows for multiple edges to exist between two nodes. So we actually could take this data set and verbatim translate it into a multi-digraph, right? Multi-directed graph. But I wouldn't, because it's a pain in the butt to iterate over however many tens of thousands of rows that we have, and I think Dan would disapprove of using dataframe.iterRows, right? Yeah, very, very emphatic yes from the front. So we won't do that. Rather, let's see how we can encode this data, this trips data, and do a bit of aggregation so that we get a, a directed graph, a plain vanilla directed graph, in which the weight between these two nodes encodes how many trips occurred between that pair of that pair of nodes. They sometimes can be equivalent, and I'm going to just show you what the equivalent case looks like, and then we can talk about the case where they're not equivalent. So for example, in a multigraph case, where I have weights of 1 encoded on there, I can actually condense this to a directed graph. Sorry, let's do directed, so we're sticking with the same example. In a directed graph case where I have multiple weight 1 edges, I can do an aggregation on the edges and say, let's just summarize it with weight 3. All right, so that's the case where it would be identical. There's other cases where it's not identical. I don't intend to do it right now, but we can talk afterwards. Okay, so we have this in memory. Let's initialize a directed graph, and we can always, and then we add in the nodes. Sorry, Dan, I have to do a iterRows call to make this happen properly. But basically, what we do is, because we know the attributes have to be encoded as a dictionary, we can take advantage of Panda's know-how, right? And we can say, if we iterate over every row, we get the row ID as like the node. The resulting leftover part of it is like a mini data frame. It's like a series. We convert that to a dictionary, and voila, suddenly now we can just take that dictionary and add it into the metadata dictionary of that particular node. So it takes a little bit of know-how to do this. It took me basically about 6 months on and off looking through this to realize, oh yeah, I probably could do this. So now you have this knowledge for free. Don't struggle through the same problem. All right? In addition to that, now we would want to say, let's say we want to know which stations are important by whatever metric, between a centrality, degree centrality, etc. Yeah, if you run this code at your own risk, there's a more efficient way to do it, in which we do a group by on the trips data frame. And we group by 2 things, not by 1 thing. We group by 2 columns at the same time, from and to station ID, and then that will give us start, stop, and the resulting data frame. And then to add the edge, the appropriate edge, we basically want the length of that aggregated data frame. That's what we're most interested in. So we're grouping them by start, stop. Some start, stop pairs will have like 20 rows. Some stop, start pairs will have like 300 rows. We just want to know how many rows there are present inside each of those. Okay, let's see. We're at 4:22. We're supposed to end. I want to end this session at 5 so that everybody can go back a little earlier. So you don't have to stick through with me blabbering on for the full 4 hours. So I'm going to skip this exercise and instead move to this one. That first exercise was just about plotting. So this exercise here, it relies on this graph G, which now you've seen how it's made, right? You've seen how it's made by looking at a pandas data frame and doing some pandas foo to make it turn it into the graph compatible data structure. So now what I'd like you to do is basically do some graph filtering, flex your muscles, and filter out edges such that they're only now in this new graph there are only edges that encode the most important trips. So like the most important edges, sorry. So those that have, say, 100 trips or more. So give that a shot. Okay, quick show of thumbs. Who's done with this one? All right, just a few. I think one hint that you might need is you might need this thing called g.copy, which creates a new graph object that is a deep copy of the original graph object. Right, so deep copy means there are no shared values in memory between those two graph objects. And if you're done with this one, go ahead and try drawing the graph, but now with the circles plot. Let's not, oh, well, actually, just draw the graph with nx.draw, but don't worry about the circles plot. It's a bit peripheral to the goals for today. Okay, so I'm going to very quickly talk everybody through the solution. First off, we create, so there are two ways of doing it. I can do it additively or in an additive fashion, or I can do it in a subtractive fashion. So I've chosen the subtractive way where I remove an edge if it doesn't fulfill the criteria. So the criteria here, so first off, we copy the original graph. We look at the original graph's edges, but then we remove the edges from the filtered graph, right, the copied graph. And that's if they don't fulfill this criteria, select count as less than 100. All right, and if we draw, you can skip the rest of the exercises. I'll just very quickly show you what it's all about. Again, highlighting the fact that hairballs are kind of bad. nx.draw gives you something that looks like this on the screen. But if you were to use a Circos plot, it looks a lot nicer, and we can actually do some nice things where we order the nodes by their connectivity to begin with. And so suddenly now we've got this thing where things of high connectivity are at the start position of the circle, and as we go around, the connectivity decreases in the original graph, right? The connectivity of the original nodes, the original graph edges. Okay. The other part that I think might come in handy for you all, so you know how to load a graph from a CSV file. You have skeleton code, basically, that you can come back to and copy and paste over and over for your own purposes. Now, what if you needed to move a graph from your computer to another person's computer? Rewriting that pandas code may or may not be a nice thing. Sometimes you might want to use the pickling capabilities of Python to serialize the entire object that exists in memory to disk such that someone else can just unserialize it into memory. And you'll preserve all of the data with very concise code. There's a caveat to doing it this way. The caveat is you never accept pickles from untrusted sources. Otherwise, you'll be loading bad code into your memory, and who knows what will happen. It might be rm-rf/. You don't want that to happen. Sudo doesn't want that to happen particularly, right? So to write to disk, NetworkX provides a write gpickle function, and then to read from disk, you can do nx.read gpickle. And down here, there's an example of when I write g to disk, I can read it back in, say I was on another notebook or in another computer. I can read that back into memory and find out that all of the metadata that I had originally encoded is present. It's all there. So there's no problems with loading and saving pickled graphs on disk. There is a slight, oh, sorry, there is one other caveat that I remember from experience. If I have 20,000 graphs and I try to pickle them to disk individually, each graph on average will take about a dozen megabytes because all of the information about that graph in memory has been serialized to disk. And that information is actually duplicated over pickled objects. So if you got lots of graphs you're serializing, I've done this before, just watch out for your disk space. All right, just watch out for your disk space. Okay, how are we doing? Half an hour left. What I'd like to do is go to this topic of bipartite graphs, but I'd like to do it in a slightly different fashion than I've done it before. This morning when I was looking through the notebook, I realized it's good for self-study, but it's not good for highlight. At the moment, it's not optimal for highlighting the high-level concepts behind bipartite graphs. So I'm going to do this entirely on the board and leave the notebooks for you to explore on your own. All right? Okay. How many of you have heard of bipartite graphs? What is the definition of a bipartite graph? That's right. So one other question then is, where would bipartite graphs have a natural real-world application? Where do you think, what comes to mind when you think of, I have two sets of things. Okay, and I'm only allowed edges between them and not within those two sets. What comes to mind? Sorry? Any type of an assignment problem. So that's the general class of it. What comes to mind for me is like Amazon, right? I'm a customer, I've made purchases. So I assign a product to a person, essentially. You can also start to imagine this case where we've got recommendation systems based on bipartite graphs. So you purchase a MacBook and now suddenly Amazon recommends that you purchase a Lenovo. Kind of a ridiculous, there's a problem with that type of recommendation system for products, but it works in some other kinds of cases where you're trying to get people assigned, say you've got people assigned to projects and you want people of similar interests to go with one another. That would be a very natural scenario for this type of recommendation problem. Okay, so for example, we can annotate this as being customers and products. If I'm now going to, so what I'm going to do here is I'm going to simplify this graph a little bit. Just give me one moment. I'm going to take out one node from each side and draw the edges as such. Everybody see that? So we have, oh yeah, let's label the customers. And label the products. So what we see here is customer A purchased 2 products, and all the other customers purchased only 1 product. Now it also makes sense that we can't have customer-to-customer edges because people don't buy people, and products don't buy products. So, pardon me? Legally, yes, sorry. oh. Let's assume we're operating in legal Cartesian space for the moment. Customers on Amazon don't buy other customers. Products on Amazon don't buy products. There is a very nice, so what we can do here is we can actually talk about relationships between customers conditioned on shared purchases. Right? So what we call this is a projection of the graph. Projection onto the customer's partition looks something like this. So the reason it looks like this is because customer B and customer A shared a purchase, which is item number 1. And so we can draw an edge between A and B conditioned on the fact that they both bought product number 1. And likewise, we do it for every other pair, and we find that it's a triangle, right? So this is what we call a projection. And a projection is useful for taking this bipartite graph and finding similar things conditioned on their connectivity to the nodes on the other partition. So I could likewise do it for products, right? Find out that some products are bought together or bought by similar groups of people, and so they would cluster together on the products projection. Okay. Now this is where we bring back a little bit of stuff from before. Do you recall that graphs have a natural matrix representation? Yeah. There's a natural matrix representation of this as well. That matrix representation would look like this. How would I fill in this matrix? What would be the first row? Be 1, 1. What's the second row? 1, 0, 1, 0. That's the connectivity matrix for the bipartite graph. And this is a very nice representation because suddenly we can do matrix math and get projections as well. And when you have really large sparse graphs, being able to do matrix math with Python becomes a really nice thing. Because there's the @ operator in Python 3.5. You all remember that, right? Python 3.5. Don't use Python 2. Okay, so people know what a transpose of a matrix is, right? That's basically swapping the rows and columns. So 1, 1, 1, 0, 1, 0. And if we do this matrix math, what's the dimensions that we get? Pardon me? 3 by 3. What's the first row going to look like? Actually, that's kind of unfair. I've calculated myself. We have, I believe it should be 2, 1, 1. I'm going to intentionally use different colors for a reason. All right? We have 2, 1, 1 in the first row. That's right. So 1 times 1 plus 1 times 1 gives me 2. 1 times 1 plus 1 times 0 gives me 1, and so on. So that's how the matrix math works. Then on the second row, I'll have 1, 1, 1. And on the third row, I'll have 1, 1, and 1. So what do the rows and columns of this matrix correspond to? They correspond to the customer nodes. And if you squint hard enough, there's a diagonal. The diagonal turns out to be the degree of the original customer nodes in the original bipartite graph. Oh, I got this wrong. Sorry. Yeah, my bad. It's that time of the day. So A was originally connected to 2 products. B was connected to only 1 product. C was connected to only 1. And if you look at the matrix, the off diagonals, that's the connectivity matrix of the graph. That's the connectivity matrix of the projection. So it all round turns out to be pretty nice and elegant. All right? If you want to see the matrix multiplication operation in action and how fast it can be in Python 3.5, sorry, how concise it can be in Python 3.5, scroll down to the end of the bipartite notebook and you'll see it in action. All right? So we can see we've got we've got these matrices, and we're doing matrix multiplication, and we're getting back these square matrices which correspond to the projection. Okay, so that's bipartite graphs that I want. That's the one thing that I want to show you about bipartite graphs in a nutshell: how they're used, how they can be used to model problems, and how we can do some fancy matrix math. And it turns out to be really elegant. Computing the projection in NetworkX, it involves iterating through like all of the, it involves iterating through Python objects, and that's kind of slow. So if you take the matrix representation, it turns out to be much faster because there's a lot of linear algebra libraries written to make this fast. They're in low-level code. But there's the trade-off. You lose the richness of information that's encoded on the original graph, right? So the original graph, every node can contain a whole lot of metadata. We lose all of that metadata the moment we go to matrices. Okay, and with that, that's the end of everything I wanted to show you. There are some bonus notebooks that are available that I invite you to take a look at your own time. Are there any questions so far? Okay, if there are no questions for now, what I'd like you to do is go to the GitHub repository. It's under my username. Or actually, you should have received this inside your email. In the README, there is a link for feedback. And I'd like to collect some feedback from you on what you thought about this tutorial and how I can make it better for future iterations. It's been a pleasure teaching you all, and I hope to hear back from you and connect with the rest of you during the rest of the time at SciPy. Thank you. Okay, and if you would be kind enough to do the feedback form, I'd really appreciate it.